please.
Okay, great to be back. Thanks for having me. So you've just heard about my work looking at the Dinkinesh flyby. This is a kind of more focused on the model itself. So this is the TEMPEST model that I've been working on for well, about 2 years now. And this is it's a Python-based model, and it's open source. So the idea is that it's something that should be quite easy to get hands-on with yourself if you have any need for a thermal model. So I'll talk you through a bit of how it works, and then a few examples of work that has been done with TEMPEST. And I'll move on to yeah, giving you a few links at the end in case you're interested in following up. So, well, you've just heard about the Dinkinesh flyby. So, as I mentioned, yeah, it's really important to understand the thermal radiance coming off this asteroid during the flyby. And so that motivated, in part, the initial development of the thermal model. It particularly motivated the inclusion of roughness later on when I realized it just wasn't going to work to try and do this without that effect built in. So TEMPEST is a pseudo 3D surface model. So what that means is one of the inputs to the model is an STL file, so a 3D shape model. And STL files are divided into triangular facets. And so for each of those facets, the model solves a 1D thermal conduction equation. So that's based on the amount of heat received from the sun, and that is dependent on the position of the facets, the way that it rotates, the way that the body rotates, and effects like shadowing from other parts of the model. And it also includes radiative mutual heating. So if you have, for example, on a concave shape, say in a crater, if you have sunlight instant on one side heating up that side of the crater, you'll have some radiant heating that heats up other parts of the crater. Now, as I mentioned, it's written in Python, which is often thought of as a kind of quick to code, slow to run type language. But it's actually, it's been possible to speed it up quite substantially. One of the things I've used to do that is Number, which is a just-in-time compiler that essentially turns that Python code into optimized machine code. So it does run very quickly. That has an optimization effect, almost 2 orders of magnitudes on this code. If you are doing anything in Python and you're not aware of it, then definitely check that out. And the other thing is that it can run in parallel, and so that's done with joblib. It's open source, so the code is available to download on GitHub. And you'll find if you go there, there's a tagged release version 1.0, which has been tested fairly thoroughly by me, but it would be great to have a few more people give it a go and use it and let me know how they get on. So if you run the model, this is the kind of one of the first outputs you'll get. So you'll have an animation of the body as it rotates. You can drag it around and have a look at the distribution of surface temperatures. And then if you right click, you can select one of the facets. So say there's a particular region that you're interested in, you can right click that and you'll get this diurnal curve pop up in the other window. And so that shows you how that temperature varies in time. Now you can convert that between the rotation angle of the parent body into local time. And so that can be quite useful. For example, if you're interested in looking at a certain body, but you don't know if it's warm enough to observe with whatever method you're using, this can be quite a good way to quickly get a feel for whether that will work. And again, it is designed to be very quick to kind of spin up, run and have a little play around with. You can see there just a demonstration of how on a body with principal axis rotation, we get much colder temperatures at the poles than we do at the equator. And the equator, we see those huge swings in temperature between day and night cycles. Now, in terms of an outline of the model, this is maybe a little bit too much to read on a slide, but I'll very happily talk to any of you about it at length if you come and find me afterwards. But like with many of these thermophysical models, the first stage is to work out after the initial setup of the code, the first stage is to work out the insolation, so the amount of sunlight received for each facet. Then there's this basically first guess of each facet's temperature, and that's based on the insolation at a particular point. That's turned out to be a very effective way of getting convergence quite quickly. So generally I found for simple bodies that don't have permanently shadowed regions and that type of thing, for example, the body will converge within about 5 or 6 rotations to 0.1 Kelvin difference between between two rotations, which I'm quite happy with. I think that's quite a quick process, and then you can leave it for longer if you want better convergence than that. You can choose two convergence methods, so you can either converge to a mean temperature difference between all of the facets on the model, or you can converge to a minimum temperature difference. So that will find the facet on the shape model that is furthest from convergence, and it'll use that as its criteria to say whether it should carry on running or not. Then in terms of steps 3 and 4, that's basically the 1D thermal model. It's based on John Spencer's thermprojrs and rewritten in Python to work with the Tempest code. Another thing to point out here is that 1D solver is modular. So if, for example, you're interested in microphysical models, looking at regolith size, particle size, that type of thing, or, for example, effects like you have with translucent materials, you can switch out that 1D solver for a different 1D solver, and the model should still run smoothly. I will caveat that by saying that I haven't yet done this, but the code is built in such a way that that should be quite a straightforward switch. And then, yeah, the model repeats until you get that convergence criteria is met. Now, the big update in the last year on this model has been to build in roughness handling. And again, this is done in a modular way. And so at the moment, the implementation is based on the work of a number of other giants in the thermophysical modeling field, some of whom we're lucky enough to have in the room with us. But it does this using this hemispherical or sphere section crater type model. And so the geometry there has been shown to quite well replicate the thermal beaming effects that we see, for example, on the moon. And so this is, again, it's done in a configurable way. So you don't have to use a full hemispherical crater. You can vary your roughness parameter by varying the crater rim angle. And then what the diagram here is showing is a way of dealing with that in 3D space that doesn't slow the model down too much. So it's not quite as slow as just multiplying the shape model by the number of facets that you're using per parent facet. You have this directional binning approach, which allows you to still compute quite quickly, but reproduce those roughness effects. And just, yeah, step 4 there is just showing what one of those spherical depressions looks like in the shape model. So you can see how, if you're looking at just the one facet of the model that you input, you're actually capturing multiple subfacets at different temperatures. And that's really important for modeling radiance and yeah, reproducing things like thermal beaming. Now, in terms of validation, the stage I'm at the moment is that the model has been quite well internally validated, and the 1D solver has been quite well validated against the John Spencer model. So the first stage in terms of internal validation is just making sure that things like energy conservation line up, and you have equivalent solutions in edge cases. So, for example, one of those is that if you run a smooth model, you should get the same result as a model that has roughness built in, but with that crater rim angle set to 0. And at the moment, the model is doing quite well with those cases. But I would like to do some substantial further validation. I know that something that's been done in the past is looking at the LRO data sets. So from Lunar Reconnaissance Orbiter, we've got really good topographic maps, and combined with the Diviner measurements, it should be possible to come close to reproducing those with this model. And I would like to have that as a kind of a seal of approval on it. So yeah, moving on to some use cases. It's great for small bodies. So as I've shown in the previous talk, modeling Dinkinesh and Salam, that's a work in progress, but it's work that, yeah, I'm feeling quite hopeful about. You can use it for asteroids. So asteroids, small bodies, comets for very quick looks, though it doesn't include sublimation at the moment. And then any arbitrary shape you like. I did this rubber duck as a bit of a joke because of the shape of 67p, and was a bit surprised to find that it broke the model. It suddenly crashed, and it turns out that beak region is in some orientations you have a huge amount of shadowing, so that the scattering can be quite substantial. I found a weird amplification effect in the scattering that was going on, so that's become my go-to for debugging. But it's yeah, it makes a nice little visualization as well. Another one that I want to flag, unfortunately, you've missed her poster, but Sarah Howes, who's with us, is a PhD student in my group and has been doing work looking at Europa and fitting thermal inertia and albedo values to Galileo measurements, and producing some really nice maps. Her poster is available online, so grab a photo of the QR code now if you would like that. And then some other kind of testing of quick ideas. This is just to show that kind of it is very quick to spin something up and have a little look at it with this model. This was something that I did over the course of a day, investigating combinations of subsurface heating and solar heating on an icy moon, and showing that if you have the right combination of both of those things, or you might think the wrong combination, you can end up with quite a confusing scenario where it's not obvious what radiance measurements what would be contributing most to your radiance measurements between those two things. And so showing that, particularly in the case of Europa, where it's comparatively close to the sun compared to the Saturn system, and has it's a comparatively dark body, solar heating becomes comparable to what we might find in subsurface heating. So if you're looking for endogenic thermal heating, this could become quite a major confounding factor. And again, I will say that this is not a science result, it's a toy model at this stage, but it gives you an idea of what's possible with this model. Now for the shameless plug. So if you are at all interested in thermal modeling, whether you do thermal modeling and you want to try using something else to check that your results align with another model, or if you have never done anything before, maybe you just want to benchmark some thermal tests, or get a feel for what temperature the asteroid that you're looking at might be in different regions, have a go. So I've done this as a quick 10-minute YouTube video, which you should be able to follow along with in real time and get the model up and running for a simple sphere model as you go. It's been used by a couple of people, and I think you should find it quite nice and easy to use. Yeah, give that a go if you like. I will also say, if you are at all interested, I'll go through to my conclusion slide. If you are at all interested in using the model, please do reach out. I'm really interested in working in kind of any field that's using this. And there's really no stupid questions here. So if you're not familiar with this type of model, or you're not familiar with Python coding and you need a bit of extra help getting it up and running, let me know. And at least until it becomes widely adopted, I'll be very happy to help you. I'll just highlight the kind of the future work section here. So one thing I'm really interested in doing is extending this to non-principal axis rotation bodies, so tumbling bodies. This came up with the recent flyby of Donald Johanson by the Lucy spacecraft, which has this non-principal axis rotation, and it's not something that very many thermal models can deal with. And it can lead to very different temperatures, particularly in the polar regions, where, as you will have seen on that Duncan model I showed earlier, the poles tend to get very, very cold. But as soon as you add in a non-principal axis rotation, they're suddenly receiving some amount of sunlight, and so that can make a huge difference to how cold they do get. As I mentioned, benchmarking against lunar data is an important next step. And then with the interest in icy moons, incorporating some kind of subsurface heat transport is in the pipeline, and something I'd love to keep working on. But yeah, if you have suggestions, and interest in using it, anything along those lines, then please do get in touch with me. I'll be at the social tonight and around for the next couple of days, and give it a go. Yeah, download it on GitHub, try running it. It's a small zip file, and it should run on a normal personal laptop, or on your huge servers at any scale that you like. And yeah, I'll leave it there. Thank you very much for listening.
Thank you.